Welcome to the video lecture on trigonometric functions using the unit circle. We're going to define our 6 trigonometric functions using the unit circle definition. But before we get there, let's consider a circle of radius 1 with the center at the origin. What would be the equation of such a circle? Well, since there's no shifts involved because our center is staying at the origin, this would just be x squared plus y squared. And since the radius is 1, this would be 1 squared, or just 1. This is the equation of what we call the unit circle. It's called the unit circle because it has that radius of 1 and it's centered at the origin. Now what we're going to do is we're going to travel around this circle. So we're going to imagine taking our unit circle, and we're always going to start at the point 1, 0. If we move with a distance t, starting at 1, 0, where t is positive, we are going to move in the counterclockwise direction from this starting point 1, 0. So if the t is greater than 0, positive, we're going to move counterclockwise around the circumference of this circle. So this t would measure this arc length as we go around our circle. So this distance right here is what we're calling t. Now the point where we stop is just some point p with coordinates x, y, and we are going to call that point the terminal point. So associated with every distance t going around our unit circle, there is a terminal point that has coordinates x, y. Now what happens if this t is negative? Well, we're still going to start at 1, 0, but this time if t is negative, we're going to travel in the clockwise direction. So we're going to go this way around our circle, and wherever we stop, based on how far that t goes, we're going to end up at some point p with coordinates x, y. So associated with this t, this distance t, there's a terminal point that has coordinates x, y. So let's take a look at what our terminal point would be if t had a distance of pi over 2. So we're going to take a look at our unit circle. We're going to start at 1, 0 on this unit circle, and we need to travel a distance of pi over 2. And since this is positive, we're going to want to go in the clockwise direction. Now we need to know how far pi over 2 is going to make us travel. So I want you to think about what the circumference of a unit circle would have to be. Remember that circumference of a circle has as its formula 2 pi r. So the circumference of our unit circle would just be 2 pi. So to go from 1, 0 all the way around the circle exactly once would be a distance of 2 pi. So what would it take to go just halfway around the circle? What would that circumference be? Well, half of 2 pi means we would be traveling a distance of pi. So to just go halfway around would be a distance of pi. What would be the distance to go just a quarter of the way around the circle? So what's a quarter of 2 pi? Well, that reduces to pi over 2, and that's exactly what our t is here. And before we finish this problem, let's also take a peek at what 3/4 of the way around our circle is. So if I went from here 3/4 of the way around, when I reduce this, 2 goes into 4 twice, so this would be 3 pi over 2. So 3 pi over 2, pi over 2, pi, and 2 pi are some very common values for t that you'll see throughout this lecture today. So you'll want to have those memorized in terms of where they land on our unit circle. So pi over 2 is a quarter of the way around the circle. So if we start at 1, 0 and we're only going a quarter of the distance around, then that means we're going to stop right here at this top point of our circle. And what would be the coordinates of that top point? Well, since this is a unit circle, we know that this is going 1 high. The x value would have to be 0, and the y coordinate would have to be 1. So the terminal point for pi over 2 is 0, 1. Now let's take a look at t equal to negative 3 pi over 2. So remember that 3 pi over 2, that was corresponding to going 3/4 of the way around our circle. But this time we want it to be negative. So we want to go in the clockwise direction. So we're going to start at 1, 0, and we're going to go 3/4 of the way around in the clockwise direction. So here's 1/4, here's 1/2, and here would be 3/4 of the way around. So again, we're stopping at that same top point on the circle, so it has coordinates 0 for x, 1 for y. Notice we got the same terminal point even though we had different values of t, and that's going to happen all the time with these unit circles, because you can go around in circles and land on the same point with various distances that you're traveling. So different values of t can determine the same terminal point. Let's talk about what happens if t is pi. So here's my unit circle starting at 1, 0, and pi was halfway around our circumference, halfway around our circle. So if I start at 1, 0 and I go halfway around, that's going to stop me right here. And what would be the coordinates? Well, this would have to be -1 for x and 0 for y. And then finally, if we let t be -6 pi, so we know that the circumference of the circle is normally 2 pi, right? Going once around is a distance of 2 pi. And we're obviously larger than that, plus we're going in the negative direction because, or excuse me, the clockwise direction because t is negative. So starting at 1, 0, if I went clockwise once around the circle, that would be a distance of 2 pi. If I went around again, that would get me up to 4 pi. And if I went around again, that would get me to 6 pi. So -6 pi lands me right back where I started. So it would have a terminal point of 1, 0, and just note here that we went 3 times around. So we got several different terminal points here. Some of them overlapped, and I just want to remind you again here that different values of t can determine the same terminal point. So different values of t can land you at the same final terminal point so that your coordinates will match. Now we're going to examine what happens for specific terminal points, and there's several here that you're going to need to memorize what the terminal point is. And the first sort of common value for t that you're going to want to have memorized is when t is pi over 4. So let's draw a picture for what this would look like. Here's my unit circle. Here's 1, 0. We know that pi over 2 is up here, so pi over 4 would be halfway between these 2 points. So pi over 4 is right in the middle here. So if I were to draw a radius going out, remember this is a unit circle, so this radius has to be 1, then what I could do is drop a perpendicular going down, and that's going to form a right angle, and what I've now created is a right triangle. The hypotenuse of this right triangle is that radius 1, and if this is our terminal point x, y, then the horizontal leg would be our x, and the vertical leg would be our y. But notice something about this circle. We know that this is 0 and this is 90 degrees, so halfway in between makes this 45 degrees. So this is a 45-degree angle, which means this upper angle must also be 45 because this has to add up to 180 degrees. So these two angles have to match. And because they're matching, that makes this an isosceles triangle. So this leg x and this leg y have to be the same. So let's call each of them x, just to show that they are equal. And then we can use Pythagorean Theorem to help us figure out what this value of x is. So since this is a right triangle, the leg squared plus the other leg squared has to equal 1. X squared plus x squared is 2x squared. If I divide by 2, I get x squared equals 2½ Take a square root of both sides. I'm only going to take the positive square root because we're talking about lengths here. So this is square root of 1/2. If you wanted to kind of clean that up a little bit, square root of 1 is 1. We have a square root of 2 on the bottom, and if I rationalize my denominator by multiplying by root 2 over root 2, then the top becomes square root of 2, and root 2 times root 2 is just 2. So this distance right here is square root of 2, and so is this one right here. So we are going over square root of 2 over 2, and we're also going up square root of 2 over 2. So that makes this terminal point root 2 over 2 for the x and root 2 over 2 for the y. Okay? So this is the terminal point for whenever t is pi over 4. And you want to memorize that correspondence. So whenever you're thinking about a pi over 4 angle, you want to think about the ordered pair root 2 over 2, comma root 2 over 2. Now before we answer some of the next questions, let's take a peek at our unit circle for a moment, and let's figure out where these pi over 4 angles would lie. Here's t being 0. The first pi over 4 would be right here. Now if I add pi over 4 to that, I'm going to get 2 pi over 4, which is pi over 2. So we know that this is pi over 2. If I add another pi over 4, that makes me have 3 pi over 4s. If I add another pi over 4, that would make me have 4 pi over 4, which is equivalent to pi. If I add another pi over 4, that would get me to 5 pi over 4. If I add another pi over 4, that gets me to 6 pi over 4, which reduces to 3 pi over 2. And if I add another pi over 4, that gets me to 7 pi over 4. And if I add one more pi over 4, that gets me back to 8 pi over 4, which is 2 pi. So the way your pi over 4s go is these sort of middle angles right here, these middle values. So pi over 1, 3, 5, 4. Excuse me, 1, 3, 5, 7 is kind of how I memorize those. So quadrant 1 is 1 pi over 4, quadrant 2 is 3 pi over 4, quadrant 3 is 5 pi over 4, quadrant 4 is 7 pi over 4. So we're going to use that to help us locate where these various terminal points are going to be. So if I want my t to be 5 pi over 4, but I want it to be negative, then that means I want to be going from the point 1, 0, and I want to be going clockwise a distance of 5 pi over 4. So instead of going this way around, we're going to want to go this way around. So remember, this would be 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, and here would be 5 pi over 4. But I'm going in the clockwise direction, so it's going to make it negative. Now think about what quadrant that landed us in. Going a distance of negative 5 pi over 4 around the unit circle landed us in quadrant 2. So the coordinates of this point, the x and the y value of this point, you can imagine drawing that little right triangle with a radius of 1. It's going to have those same two equal legs because this is a 45-degree angle here and here. So this is still root 2 over 2 and root 2 over 2, but because we're in quadrant 2, all we have to worry about are what signs this should have. So the terminal point will still have the same values, root 2 over 2 and root 2 over 2, that we had for pi over 4 in quadrant 1. The only difference is because we landed in quadrant 2, in quadrant 2 the x value should be negative and the y value should be positive. So by memorizing this terminal point for pi over 4, you know the terminal point of every pi over 4 angle out there. All you have to do is adjust the signs to fit the quadrant that you end up in. So here would be my final solution for that terminal point. Let's try another example. So this time we want to go to 7 pi over 4, and that's positive. So here would be 1 pi over 4, 2 pi over 4, 3, 4, 5, 6, 7. So 7 pi over 4 would land me right here. And that is in quadrant 4. So automatically, because it's a pi over 4 terminal or t value, I know that my terminal point has to be a root 2 over 2, comma root 2 over 2. But since I'm in quadrant 4, the y value this time is negative and the x value is positive. So just adjusting my signs to fit the quadrant that we land in. Okay, let's try one more example here. Let's try 3 pi over 4. It's positive, so we're going to go 1 pi over 4, 2 pi over 4, 3 pi over 4. So that's going to land me right here, which is in quadrant 2. Because it's a pi over 4 angle, I know this is going to be root 2 over 2, comma root 2 over 2, but because it was quadrant 2, the x value should be negative and the y value should stay positive. Okay, so the first terminal point that you need to memorize are these root 2 over 2's, and they are associated with every pi over 4 t. The next common t value that we're going to memorize is whenever t is a pi over 6 type of angle. So let's draw what this would look like. Here's our unit circle, and pi over 6 is between 0 and pi over 2, and just so that you can kind of see what it's equivalent to in terms of a distance around the circle, let's convert it to degrees. So pi over 6 is in radians, so in order to convert that to degrees, we're going to need to do a little conversion. So this is radians. So to get rid of the radians and change it to degrees, I would have to do a conversion factor like this, and we know that there are 2 pi radians in every 360 degrees. So to simplify this, 6 goes into 360 60 times, pi divided by pi cancels out, and we're left with 60 over 2, which reduces to 30 degrees. So pi over 6 radians is equivalent to 30 degrees. So if I go pi over 6 this direction, what that means is when I extend this radius out, this little central angle is 30 degrees. And I'm going to drop a perpendicular down, and I'm going to use this as my x and this as my y, because those are the coordinates of my terminal point. So let's draw this little triangle. We have a 30-degree angle here. This is my right angle. This is 1. Because this is 30, that forces this to be 60. Now, if we wanted to figure out what these side lengths were going to be, there's a little geometry that we're using. And this actually comes from an equilateral triangle. If you can visualize just doubling this down like this, what we would have is an equilateral triangle where this is 1, and this is 1. We're doubling this angle so that if this much is 30, then the whole thing is 60, which makes this 60 and this 60. And because this whole side here is 1, then that makes half of it equal to a half. And so if we called this x, then x squared plus a half squared would have to equal 1 squared for this right triangle right here. And if we solve this, we get x squared plus a fourth equals to 1. If I subtract the 1/4, I get 3/4. And if I take a square root of both sides, I'm going to get square root of 3 over 2. So this distance right here is root 3 over 2, and this was half of that full length 1. So what we end up with is this horizontal distance, which is our x coordinate, is root 3 over 2. And this vertical distance, which is what our y value is 1/2. So the terminal point associated with pi over 6 is root 3 over 2, comma 1/2. And this is something that you want to have memorized, because every single pi over 6 angle is going to have this same terminal point, except that the signs may change depending on which quadrant you are in. So this would be for quadrant 1. If I'm in quadrant 2, 3, or 4, then I would just adjust my pluses and my minuses. Now, before we answer some of these questions, let's also visualize where these pi over 6 angles would be and what they're called. So if we think about 0 is right here, pi over 6 would be right here, 2 pi over 6 reduces to pi over 3, and that's equivalent to 60 degrees. 3 pi over 6 is pi over 2. 4 pi over 6 reduces to 2 pi over 3. 5 pi over 6 is right here. 6 pi over 6 is pi. 7 pi over 6 would be here. 8 pi over 6 reduces to 4 pi over 3. 9 pi over 6 reduces to 3 pi over 2. 10 pi over 6 would be here, and that would be equal to 5 pi over 3, and 11 pi over 6 would be here. 12 pi over 6 would get you back to 2 pi. So the pi over 6's, the ones that don't reduce to pi over 3 angles, would be pi over 6, which is right here, 5 pi over 6, which is over here, 7 pi over 6, and 11 pi over 6. So it's these close angles to the x-axis. And it goes 1, 5, 7, 11. 1, 5, 7, 11. So you want to try to memorize the placement and position of those common pi over 6 angles, because you'll see them happening a lot. So for example, if I wanted my t to be negative 7 pi over 6, 7 pi over 6 is normally in quadrant 3 over here, but we want to go in the negative direction. So starting at 1, 0, 1 pi over 6 in the negative direction would be here. Then this one over here would be 5, and this one over here would be 7. So negative 7 pi over 6 would put me right there in quadrant 2. Now because it's a pi over 6 t value, I automatically know the terminal point is got to be a root 3 over 2 comma 1/2, but it might have some negatives in there depending on which quadrant I'm in. And if I'm in quadrant 2, the x is always negative, the y is always positive. Okay, so let's take a look at the next one here, 11 pi over 6. So if I draw my unit circle, this is a positive, so here's 1 pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. So I would start here and go counterclockwise around until I hit that t value. And because it's quadrant 4, then my terminal value is going to be root 3 over 2 comma 1/2, and in quadrant 4 the y is negative and the x is positive. And then finally 7 pi over 6, positive, so here's 1, 5, 7, so this is 7 pi over 6 going in the counterclockwise direction. That landed me in quadrant 3, so my terminal point is root 3 over 2 comma 1/2, but in quadrant 3 both of those should be negative. So you can be asked a lot of these questions and be able to get a lot of answers just from that one basic terminal point where all you're doing is adjusting the signs. Okay, one last common terminal point that you do want to know about as well is the t equal to pi over 3 value. And we're going to get that using symmetry from this t equals to pi over 6 that we just talked about. So let's visualize where pi over 3 would be. And in terms of converting to degrees, just so you can see what it's equivalent to, if I convert pi over 3 to degrees, 360 degrees in 2 pi radians. So if I reduce here, 3 goes into 360 120 times, 120 over 2 is 60 degrees. So pi over 3 is up here, where this angle is 60 degrees. And if I drop my perpendicular down and call this x and call this y, then I have this triangle that looks like this. The radius is 1, so that's this hypotenuse side over here. Now to get our x and our y, you can just visualize creating this equilateral triangle where this side is 1 and this whole side is 1. So that forces this x to be half of this 1, and solving that Pythagorean theorem like we did in the last problem, that would tell us that this y value would be root 3 over 2. So it's the same exact relationship or ratio that we got for the earlier value of t of pi over 6, because this is just a 30, 60, 90 right triangle. And the ratio of the sides always fits this same 1 for the hypotenuse, 1/2 for the shorter leg, and root 3 over 2 for the longer leg. So my ordered pair this time has x equals to 1/2 and y equals to root 3 over 2. So again, it's exactly the same value and terminal point for pi over 6, but it's reversed. This time the 1/2 comes first and the root 3 over 2 comes second. For pi over 6, you just swap that. So every pi over 3 angle is going to have this same terminal point, except with possibly different signs depending on which quadrant we're in. Let's visualize what all of our common pi over 3 angles are going to be. So here's 0. 1 pi over 3 is that 60 degrees. 2 pi over 3 is over here. 3 pi over 3 is the same as pi. 4 pi over 3 puts us here. 5 pi over 3 puts us here. And 6 pi over 3 gets us back to 2 pi. So we're just chopping this circle up. So it's 1, 2, 4, 5. 1, 2, 4, 5. So you want to kind of memorize those 4 different pi over 3 angles because you'll see them a lot. So let's take a look at this next example. We want t to be negative 7 pi over 3. And that wasn't one of our 4 values that we just talked about. And that's because 6 pi over 3, remember, got us back to 2 pi. So 7 pi over 3 would be beyond that. So let's figure out where this is going to be. The other complication here is that it's negative. So we actually want to be figuring this out in the negative direction. So starting here and going clockwise, here would be negative pi over 3, negative 2 pi over 3, negative 4, negative 5, negative 6, and then negative 7 would get me right back to this position. So we're going all the way around once, and then we're going a little bit further and stopping right here. Which quadrant did we stop in? We stopped in quadrant 4. That's really all you care about. You don't really need to know exactly the specific point where it is. You just need to know what quadrant you ended up with. And because this was a pi over 3 angle to begin with, I automatically know its 2 coordinates of its terminal point have to be 1/2, comma, root 3 over 2. And because I stopped in quadrant 4, the y coordinate should be negative, the x coordinate stays positive. Okay, so let's try 11 pi over 3. Again, I automatically know that the ordered pair has to be a 1/2 and a root 3 over 2, and then we just need to figure out what quadrant 11 pi over 3 ends up in. So this is a positive value, so we're going to go counterclockwise. Here would be 1 pi over 3, 2 pi over 3, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 pi over 3 puts us here. And we actually went all the way around once, and then we came back and stopped right here. So 11 pi over 3, actually look at what happened. It's equivalent to where we landed in the last example, because we're still in quadrant 4. So in quadrant 4, the y value is negative, the x value stays positive. Okay, the last one here is 2 pi over 3. So here's 1 pi over 3, and then this would be 2 pi over 3. So 2 pi over 3 would stop us right here, which makes us stop in quadrant 2. So our terminal point is 1/2 for the x, root 3 over 2 for the y, and in quadrant 2 the x is negative and the y is positive. So as you can see from the above examples, the terminal point of any number always relates back to the corresponding terminal point in the first quadrant, and all you're doing is adjusting the signs so that they fit the quadrant that you ended up with. Now the next thing we're going to talk about is something called a reference number. So we're going to let t be a real number, and then we're going to say that the reference number, t bar, and that's what this notation means, t bar, associated with this t is the shortest distance along the unit circle between the terminal point determined by t and the x-axis. So this is kind of confusing, but what t bar is really measuring is it's measuring the angle between t and the closest part of the x-axis, and it should always be a distance between 0 and pi over 2. So let's take a look at an example, and you'll be able to understand what I'm talking about when we draw our picture. So we want t to be 5 pi over 6. So let's draw that first. So we're going to start at 1, 0, and 5 pi over 6 would be, here's 1 pi over 6, 5 pi over 6 is over here, quadrant 2. So t equal to 5 pi over 6 would be this whole distance around our circle. Now what does this t bar represent? Where did we stop? We stopped right here. What would be the shortest distance along the circle from where we stopped to the closest part of the x-axis? Well, since we're in quadrant 2, the closest part of the x-axis to get there would be this distance right here. So this distance from the x-axis up to that stopping point, that is called your t-bar, your reference number. And what we want to figure out is what it is equivalent to. So t-bar here would be what amount, what distance? Well, we know that to go from this point all the way over to the negative x-axis, that's an entire distance of pi. But we're only going from 1, 0 to 5 pi over 6. So the distance in between here would be pi going all the way down to that negative axis minus 5 pi over 6. So pi minus 5 pi over 6, let's get a common denominator. Pi is 6 pi over 6. So when I subtract 5 pi over 6 from that, that makes t bar equal to 5 pi over 6. So in other words, this little distance right here is a distance of pi over 6. So what we could do then is say that the reference number for this terminal point is a pi over 6 angle. Okay? Let's try another example here. So suppose we wanted t to be 5 pi over 4. So first you want to locate where that angle, where that stopping point is. So 5 pi over 4, here's 1 pi over 4, here's 3 pi over 4, here would be 5 pi over 4. So 5 pi over 4 means we're going to go all the way to here. Now, where we stopped was right here. Now imagine the distance from that stopping point to the closest part of the x-axis. Since we're on this half of the circle, the closest part of the x-axis would be the negative x-axis. So the closest distance from that x-axis to our stopping point would be this distance on our circle. That is our t-bar. So to figure out how short or how much that t-bar actually is, because it's not the entire 5 pi over 4, it's just this little distance right here, how could we figure out what just this little piece is right here, just what this distance is? Well, you know that 5 pi over 4 goes beyond pi. So what we're going to do is we're going to take that 5 pi over 4 and we're going to subtract off this pi part, this top half right here. And if we take all of 5 pi over 4 and we subtract off just this top part, we should be left with just this blue part down here. So our reference angle t bar is the entire distance 5 pi over 4 minus the pi. Let's get a common denominator. 4 pi over 4 is the same as pi, so 5 pi over 4 minus 4 pi over 4 is equal to pi over 4. So we would say that our reference angle is pi over 4. So the value of the terminal point of this stopping point would be the same terminal point as this pi over 4 angle, but we would adjust it to be in quadrant 3 because that's where this ending point stopped. Alright, let's try another example. So this time our t is negative 5 pi over 3. So let's first locate where that would be. Now it's a negative angle, so we want to go clockwise. Here's negative 1 pi over 3. It would be negative 2 pi over 3. Negative 3 pi over 3 would be here. Negative 4 pi over 3 would be here. And this would be negative 5 pi over 3. So we're going from here all the way around to here. So that's our t. So what would our reference angle be? Well, this time we're on this half of the circle. So the closest part of the x-axis would be the positive x-axis. So from the place where we stopped down along the circle to that positive x-axis, this distance right here is what our t-bar is supposed to represent. So how could we figure out what t-bar equals? Well, we know that to go all the way around would be 2 pi. But we want to subtract off from that 2 pi this distance of 5 pi over 3. So we're going to take 2 pi and we're going to subtract off 5 pi over 3 to see how much little extra, this little blue arrow, it would take to go all the way back to 2 pi again. So we're taking 1 full revolution minus this almost full revolution to figure out how short we are, and that's this blue arrow. So let's get a common denominator of 3. 2 pi would be 6 pi over 3. So 6 pi over 3 minus 5 pi over 3 is pi over 3. So t-bar, this little distance right here, is pi over 3. So the reference angle for negative 5 pi over 3 would be 5 pi over 3. Alright, the last example that we're going to do looks a little bit strange because it doesn't look like one of our common angles, our pi over 3s, pi over 4s, or pi over 6s. This is just a number negative 2. So we need to figure out where negative 2 would land on our circle. And in order to figure that out, you need to have a rough sense of the size of some of our common t values. So, for example, how much would just pi be around our circle? Well, pi is approximately 3.14, right? So pi would be about 3. What would pi over 2 be? Well, that's about 1.5, about half of 3. So 2 is somewhere in between those. All right, that's how I kind of figure this out. So 2 is somewhere between a pi over 2 and a pi, but we want to go in the negative direction. So if I started here at 1, 0, and I went clockwise pi over 2, that would stop me here. And if I went clockwise to pi, that would stop me here. So negative 2 is somewhere in between. And I don't necessarily know exactly where it is. I just know that it has to be somewhere in this quadrant 3. So this is our t equal to negative 2. So what would our reference angle look like? How would we draw that? Well, we stopped here in quadrant 2, so that means we're going to be closest to the negative x-axis up here. So the distance from that negative x-axis to where we stopped along our circle would be this distance right there. So that's your t-bar, that little blue arrow. So how do we figure out how much this t-bar is? Well, we know that to go from here to here would be a distance of pi. I'm ignoring minus signs temporarily. So this whole distance would be pi, and what I want to do is take away the 2, take away this much, which was negative 2. And that should leave me with this little blue arrow. So to get my t-bar, I'm going to take the whole distance pi minus the 2, and you can't really reduce that because these are not like terms. The 2 doesn't have a pi next to it. If you wanted to get a decimal for this, pi is, 3.14159, so if I subtract 2 from that, this is going to be 1.14159. So we could give an approximate value, or we could just leave it in terms of pi. So these terminal points and these reference angles are a little bit tricky sometimes. What you want to do to find a terminal point is first draw your t, your normal t, and then you're going to sketch in where that terminal point t-bar is by measuring where you stopped up to the closest part of the x-axis. Find out what that reference number is, and then to get the terminal point for this t, it's going to be based on whatever the terminal point is for your reference angle, and then you just adjust the signs based on what quadrant you ended up in. And here's a picture to help you visualize what all these t-bars would look like. And I won't talk through all of them, but for example, in quadrant 1, your t and your t-bar would be exactly the same thing. In quadrant 2, your t, if this is assuming that t is positive, if your t goes all the way to something in quadrant 2, then your t bar would be this little blue piece right here, and to find its value, you would just take pi minus whatever the original t was. Okay? And in quadrant 3, if your t goes all the way to something in quadrant 3, to find t bar, you would just take this whole t value, which is bigger than pi, and subtract off pi to get this little blue piece. And finally, in quadrant 4, your t bar would be from the positive x-axis down, so to figure it out, just take one full revolution to pi, subtract off t, and that'll give you this little blue piece. So that's for all the t's if they're positive. And then you would do something similar if they're negative, and those are written down below. I won't talk through all of those. Okay? So here are the major terminal points that you want to have memorized. So obviously if t is just 0, then we're at 1, 0. That's starting point on our unit circle. For any pi over 6 angle, its terminal point will be root 3 over 2, 1/2. For pi over 4, it's root 2 over 2, root 2 over 2. For pi over 3, it looks just like pi over 6, but swapped. The 1/2 comes first, then the root 3 over 2. And if you're at a pi over 2, which is like that 90 degrees, then you'd be at 0, 1. So these are all your reference angles, your terminal points for these reference angles, and you would just adjust the signs depending on which quadrant you ended up in. So let's try some values here. So first we want our t to be 7 pi over 3. So we need to locate where that would be so we know which quadrant we're in. Now automatically I see that 3 in the denominator, so I know in advance here that this is going to have this terminal point with possibly some different signs. So right off the bat, because of that 3 in the denominator, I know this is a 1/2 for x and a root 3 over 2 for the y. Then it's just up to me to figure out what that reference point is and figure out what my quadrant should be so that I can adjust my signs. So let's figure out where we are. So this is positive, so we're going to go counterclockwise. Here's pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3, 7 pi over 3. So we're going all the way around 1 full time, and then we're going an additional pi over 3 beyond that. So which quadrant did we end up in? We ended up in quadrant 1. And if you wanted to draw it in, this piece right here, that would be your t bar. So your t bar would just be that extra pi over 3 that we had to go beyond 2 pi. So since we're in quadrant 1, that makes both of these coordinates needing to be positive. And that's it. Okay, let's try the next one. Now we want 13 pi over 6. So here's 1 pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6, 12 pi over 6 is 2 pi, so 13 pi over 6 would be right here. So we're going all the way around once, plus an additional pi over 6. So again, your t bar would just be that little extra beyond 2 pi that we had to go. So t bar here is pi over 6. And because we ended up in quadrant 1 again, then we want positive x's and positive y's. Because this is a pi over 6 reference angle for our t bar, that means we want root 3 over 2 to come first, then the 1/2, and we said that this was quadrant 1, so both of these should be positive. Okay, 31 pi over 3. Now you can start counting all the way around your circle like we've been doing on these last examples, but hopefully you see that this 31 is pretty big, so we would have to count around several times before we get to 31 pi over 3. So sometimes when the number's big like this, I just do a little dividing to help me figure out how many times around I'm going and what the extra would be. So for example, you know that 3 goes into 31 10 times, and it would leave you with a remainder of 1. So that means this is like 31 pi over 3 is equivalent to a 30 pi over 3 plus that additional pi over 3. And 30 pi over 3 is just 10 pi. So 10 pi is the equivalent of going 5 times around your circle, because each time is a 2 pi. So I would go 2 pi, 4 pi, 6 pi, 8 pi, 10 pi, and then I would go that additional pi over 3. So we're really going 5 times around plus an additional pi over 3. That's what this means. So our t-bar, our reference point here, is that extra pi over 3 that we had to go. And just like all the other ones, this ended us up in quadrant 1. So because it was a pi over 3 reference number, we're going to have the 1/2 coming first, then the root 3 over 2, and in quadrant 1, both of these are positive. Okay, one more example like this. Again, I have a really large number in my numerator, so let's do a little bit of dividing. First, 3 goes into 73. Well, we know 3 goes into 7 twice, and 3 goes into 13 4 times with the remainder of 1. So that means that 73 pi over 3 is the same as 24 pi plus that remainder of pi over 3. We had a 1 pi over 3 left over. So we want to go 24 pi, which if you divide that by 2, that would be 12 times around our circle. But remember, this was negative, so we're going clockwise this time. So I'd go around the circle 12 times around, plus that additional pi over 3 in the clockwise direction. So we loop around 12 times this way, and then we do that extra little remainder, and that would leave me off right here at negative pi over 3. So my reference number would be this distance right here, this t-bar, and that's equal to pi over 3, that little extra remainder that we had. And this time we stop in quadrant 4, because we were going in the clockwise direction. So since this is a pi over 3 angle, the 1/2 has to come first, then the root 3 over 2, and in quadrant 4 the y value is negative, the x is positive. Okay, so we've talked a lot so far about these terminal points, these common terminal points that you want to have memorized. And you want to be able to find reference numbers and figure out what quadrant you're in. And the reason behind all that is because based on those terminal points and these real number t's, we are now going to be able to define what our 6 trigonometric functions are. So here's our definition of our 6 trig functions. If t is any real number and p is the corresponding terminal point on the unit circle determined by t, then we're going to define the sine of t to be that y coordinate of our terminal point. And we're going to define the cosine of t to be the x value of that terminal point. And then the other 4 are determined by those x's and those y's. So tangent of t is the y coordinate over the x coordinate. Cosecant of t is 1 over the y, so 1 over the sine. Secant of t is 1 over the x, or 1 over the cosine. And cotangent of t is x over y, which is just the reciprocal of tangent. Okay? So the main 3 are these top 3, and then the other 3 below it are the reciprocals of the ones above. So let me show you what this really means now. So suppose that you're given t is equal to 5 pi over 6. Let's draw that picture. So we know that pi over 6 is here, 5 pi over 6 lands us in quadrant 2. So here's 5 pi over 6, and that has, for its t-bar, this little distance right here, and it would have as its reference point pi over 6, which is in a quadrant, but 5 pi over 6 was in quadrant 2. So what would be the terminal point associated with a pi over 6 angle that's in quadrant 2? Well, pi over 6's always have root 3 over 2 coming first, then the 1/2, and in quadrant 2 the x is negative and the y is positive. So this is all stuff we've already done. Now let's add in our new stuff. So now what I want to know is what would be the sine of 5 pi over 6? What would be the cosine of 5 pi over 6? What would be the tangent of 5 pi over 6? What would be the cotangent of 5 pi over 6? The cosecant of 5 pi over 6 and the secant of 5 pi over 6. So let's figure out these first three. By definition, the sine of this 5 pi over 6 is just the y value of our terminal point. So sine of 5 pi over 6 is equal to 1/2. The cosine of 5 pi over 6 by definition will always be this x value, so negative root 3 over 2. The tangent is the y value, which is 1/2, divided by the x value. Now since these both have 2's in the bottom, those are going to cancel out. So this is 1 over negative root 3, and if you wanted to rationalize that by multiplying by a root 3, you'd get root 3 over 3, and there's still that negative floating around. Now those are the major three. The other three trig functions are just the reciprocals of these. So you want to remember that cosecant, CSC, is the reciprocal of the sine. So if sine was 1/2, then cosecant is just 2. Secant is the reciprocal of cosine. So if cosine is negative root 3 over 2, then secant would be negative 2 over root 3. And you could rationalize the denominator here and get negative 2 root 3 over 3. And then finally, cotangent is the reciprocal of tangent. So if our tangent was negative root 3 over 3, when I flip that over, I get negative 3 over root 3. And when I rationalize, we get negative 3 root 3 over 3. The 3's cancel. So this is negative square root of 3. So here are my 6 trig values, and they come from just the x and y coordinate or some manipulation of those x and y coordinates. Alright, so let's try another example. T equal to pi over 3. So the first thing you're going to want to do before you figure out these 6 trig functions is first visualize where pi over 3 is. It's right up here at that 60 degrees. So the t bar is the same exact angle, so that's also your t bar. And we're in quadrant 1. So what is our terminal point for a pi over 3 angle in quadrant 1? Pi over 3's have the 1/2 coming first and the root 3 over 2 coming second. So now we should be able to find all of these 6 trig functions. So sine of pi over 3, cosine of pi over 3, tangent of pi over 3. Let's start with those 3. Sine of pi over 3 is always the y value, so this will have to be square root of 3 over 2. Cosine of pi over 3 is always the x value, so this would just be 1/2. And tangent of pi over 3 is the y value over the x value. And again, the 2's are going to cancel out, so this is just root 3. Then to get the other 3, you use your reciprocals. So the reciprocal of sine is cosecant. So when I flip over root 3 over 2, this becomes 2 over root 3. If you want to rationalize, that would be 2 root 3 over 3. Reciprocal of cosine is secant, and the reciprocal of 1/2 becomes a 2. And the reciprocal of tangent is cotangent, and the reciprocal of root 3 would be 1 over root 3, and if you rationalize, that would be root 3 over 3. Okay, let's try one more example here. This time we want our t to be negative pi over 2. So remember, pi over 2 is like 90 degrees, but we're going in the negative direction, so we want to go clockwise. So starting here, we want to go 90 degrees, so that's going to stop us right here. on that quadrant. These are called quadrant angles when they line right on the x or the y axis. So negative pi over 2 has what as its terminal point? Well, the x value is 0 and the y value would be negative 1. So we want to know what the sine of negative pi over 2 is, the cosine of negative pi over 2, and the tangent of negative pi over 2. So the sine of negative pi over 2 is the y coordinate, so that would be negative 1. The cosine is always the x coordinate, so that's just 0. And the tangent is the y over the x. And notice here that that causes us to divide by 0. So the tangent of negative pi over 2 does not exist. It's undefined. So I'm just going to put 0 with a slash through it. Let's take a look at our reciprocals. So the reciprocal of sine would be cosecant, and the reciprocal of negative 1 stays negative 1. The reciprocal of cosine would be secant, and if I flip over 0, I'd get 1 over 0, which is also undefined. So this time the secant also does not exist. And then the cotangent is going, instead of being the y over the x, this time it's going to be the x over the y. So we would have the 0 over the negative 1, and 0 divided by negative 1 is going to stay 0. So the tangent was undefined, but the cotangent is 0. Okay, on the next page here, we have our table of some of these most common values. You pretty much want to have these memorized because they're going to occur so often that it's good to just be able to spit them right out and not have to think about it very much, because you're just going to need to know these really, really well. So knowing the sines, cosines, tangents, cosecants, secants, and cotangents of all of those major quadrant 1 angles, 0, pi over 6s, pi over 4s, pi over 3s, and pi over 2s. So you want to have this table memorized. And just to kind of remind you, there is a PDF file available on D2L that shows the unit circle, and this is what it looks like, and it shows all of those pi over 6, pi over 4, pi over 3, pi over 2, and so on. And then it shows the equivalent of those in degrees, so 30, 45, 60, 90 degrees. And it also shows all of the terminal points with the corresponding pluses and minuses depending on which quadrant you're in. So you definitely want to have this unit circle memorized because you're going to be using these values so often. You don't want to be wasting your time having to try to figure out what these terminal points are every time. So just be able to spit them right out without having to think about it. Now, if if this terminal point P, which is your x comma y, is the terminal point for any number t, then theta is the angle in standard position measured in radians whose terminal side is the ray from the origin through P. So let me draw a picture of what I'm talking about here. Here's our unit circle. If this is our t, this distance around our circle, and our terminal point P is this x comma y, then what we're saying is theta is this central angle from the positive x-axis up to where that terminal point is if I draw this little ray going out. So theta would be this angle in standard position. Now notice that we're on a unit circle, so your radius is 1, and you should remember from an earlier lecture that arc length s is equivalent to the radius times theta. So in our problem, what we're calling this arc length is t. So instead of calling it s, we're calling it t. So this s would be t. Our radius is 1, and theta we're going to call theta. So what that shows us is that when we're on a unit circle, this t is exactly the same value as theta. So this is true on a unit circle. And that's why I occasionally mess up when I'm talking and I call this t an angle, because it's equivalent to this standard angle in standard position. So t and theta are synonymous. So when you talk about sine of t, this distance around your circle, you could also be referring to sine of theta, that central angle in between. And cosine of t is the same as cosine of theta, tangent of t is the same as tangent of theta, and so on. since the values of the trig functions of an angle theta are determined by the coordinates of our terminal point, the units on theta are irrelevant. So that means this theta could be in degrees or it could be in radians, and you'll see questions where it goes back and forth. So be able to handle finding trig values when the angle theta is in degrees or in radians. Be able to go back and forth. So we're going to finish up today with just some random trig expressions that I'm asking you to find the exact value of. So most of these you should be able to find out by hand without using a calculator at all. And you're going to be able to do that by using that unit circle and by thinking about what the correct terminal point would be that corresponds to your angle theta or your arc length t that you're talking about. So let's take a look at this first one. We want cosine of 5 pi over 4. So to figure this out, the first thing that you're going to want to do, and we're doing this by hand, we're not using a calculator, would be to figure out where 5 pi over 4 is on a unit circle. So we know pi over 4 is here, 2 pi over 4 is the same as pi over 2, 3 pi over 4, 4 pi over 4, here's 5 pi over 4. So this is our distance around. There's our t. Now what is the corresponding terminal point using the correct signs based on the fact that this landed us in quadrant 3? Well, since it's a quadrant 3 angle and it was a pi over 4 angle, we know that it has to have root 2 over 2's, because every pi over 4 angle has root 2 over 2 comma root 2 over 2, and in quadrant 3 both of these should be negative. Now the last thing we do is we have to remember which of these coordinates is a cosine. Cosine is always the x value. So if this is my terminal point, then my x coordinate is negative root 2 over 2, and that must be the cosine of 5 pi over 4. Okay, so let's take a look at sine of 135 degrees. So you need to figure out what 135 degrees is. You can use your unit circle to help you out. You can see it's right here. 135 degrees is equivalent to 3 pi over 4. If you didn't know that, you would have to convert it. So you could do, 135 degrees and multiply by 2 pi radians equals 360 degrees, and do your conversion, and what you'll see is that this comes out to 3 pi over 4. So you need to know the corresponding degrees with their corresponding radians. You have to be able to convert back and forth pretty quickly. So 135 degrees is the same as 3 pi over 4, and 3 pi over 4 is right here. So this is the same as 135 or 3 pi over 4. So the t bar would be this distance here, and that makes this a pi over 4 angle. So its ordered pair for its terminal point has to be root 2 over 2 comma root 2 over 2, but we're in quadrant 2, so the x value is negative, the y value is positive. Now what does the sine correspond to? Sine is always y, so we want this y coordinate, so this would be square root of 2 over 2, and it's positive. Okay, let's take a look at 315 degrees. So we need to know where that is, and again, you can get that from your unit circle. You should know that 360 degrees would be all the way around the circle, so 315 would be 360 minus 315 is 345, or 45 degrees difference. So 315 is right here. And I'll show you on the unit circle again. 315 is right here. Okay? So if I convert to radians, you can certainly do that, or just know that this is a difference of 45 degrees right here. So this would be a 45 degree angle. You can think of it that way as well. But what you also want to realize is this is equivalent to a pi over 4 angle, because that's what this t bar would be. T bar is pi over 4. If you converted, 315 is the same as 7 pi over 4, because this would be 1, 3, 5, and 7. So no matter how you think about it, you need to know that you're dealing with a pi over 4 angle, so it's a root 2 over 2, comma root 2 over 2, and 315 degrees lands you in quadrant 4. So your y value should be negative, your x value should be positive. So no matter how you get there, this is what you need to come up with, this terminal point with the correct signs. Once you get to there, then you know that your tangent is y divided by x. So I'm going to do negative root 2 over 2, that was my y value, divided by my x value. These are exactly the same on top and bottom, so they're going to cancel out, but I'll be left with that negative. So this is just negative 1. Okay, let's try cosecant of negative 60 degrees. Now 60 degrees, that's one of these common angles that you want to be familiar with. 60 degrees is the same as pi over 3, but we're going in the negative direction. So we're going to go negative pi over 3 right here. So what quadrant did we end up in? We ended up in quadrant 4, and our t-bar is this pi over 3 reference number. And because it's a pi over 3 angle, the 1/2 comes first, the root 3 over 2 comes second, and in quadrant 4 the y value is negative. Now we have to think about cosecant. Cosecant is the reciprocal of sine. Sine is y, so cosecant should be 1 over y. So we want the reciprocal of this y value. So if I flip over this y value, it becomes negative 2 over root 3. Now I personally, as an instructor, am not too worried about you rationalizing denominators. Usually textbooks always will, so it's a good idea to know how to do that rationalizing. But to me, it's okay if you just left your answer as negative 2 over root 3. Other instructors may feel differently, so it depends on who your teacher is. Okay, so let's try cotangent of 5 pi over 3. Now this is one we have talked about today. Pi over 3 would be here, 2 pi over 3 would be here, 3 pi over 3, 4 pi over 3, 5 pi over 3. So 5 pi over 3, it's positive, so we're going counterclockwise, lands me right here. My reference number would be this t-bar, which is a pi over 3 angle, and it's in a quadrant 4. So pi over 3's have 1/2 coming first, then the root 3 over 2, and in quadrant 4 the y value is negative. Now cotangent is the reciprocal of tangent. Normally tangent is y over x, so cotangent is going to be x over y. So we're going to take this x value, 1/2, and we're going to divide it by this y value, negative root 3 over 2. The 2's on the bottom cancel out, so this is negative 1 over root 3. I'm happy if you leave it like that, but if you rationalize the denominator, it's also the same as negative root 3 over 3. Okay, secant of 210 degrees. So a couple ways to think about it. You can convert it. You could multiply this by 2 pi over 360 to convert to radians. You could see that 210 is 180 degrees, which is pi, plus an additional 30 degrees, which is a pi over 6. So this on your unit circle should be right here. In quadrant 3, 210 degrees is the same as 7 pi over 6. So no matter how you think about it, you need to draw a picture and show that it's going to go 180 plus that additional 30, so it's going to land you right here at 7 pi over 6, or 210 degrees. So my reference angle is this little distance here, that t-bar, and that t-bar is a pi over 6 angle, but we're in quadrant 3. So my terminal point for pi over 6 would be root 3 over 2 for the x, 1/2 for the y, and in quadrant 3 they're both negative. And then finally we want a secant, which is the reciprocal of a cosine. Cosine is normally x, so secant would be 1 over x. So I want the reciprocal of this x value. So I'm going to flip it over, so it becomes negative 2 over root 3. And you can leave it like that, or if you rationalize, it's negative 2 root 3 over 3. Okay, the last few values here should look a little bit different because none of these angles are going to be some of the nice ones that you are expected to have memorized. So 48 degrees, when you convert that to radians, it's not going to end up being any of these nice angles on my unit circle. All of these end in either a 5 or a 0. Likewise, 21 degrees is not on there. 5 pi over 12 is not a pi over 3, a pi over 4, or a pi over 6 angle, so it's not one of the ones we have memorized. And then these are just decimals, which aren't any nice decimals either, so these we would all have to do using our calculator. So for these last 6, because they're not the ones on your unit circle, you would be allowed to use your calculator to figure these out. So for the first one here, it's just a real simple task of using your calculator, but the one thing that you need to make sure of is the fact that you're in the right mode. This is a degree, so you want to make sure that you convert your calculator to degree mode first before you type in cosine of 48. So let's pull up the calculator. To change your mode, just press mode, and the default is usually radians. So on mine, that's already highlighted. So I'm going to need to arrow down and go over to degree and hit enter. So now it's expecting me to type in angles in terms of degrees. So then I'm just going to quit out of here and I'm going to type in cosine of 48. It's expecting that 48 to be in degrees, so this would be 0.6691. Okay, so for cosecant, if you notice on your calculator, there is no cosecant button. There's only sine, cosine, and tangent. So to figure out cosecant of 21, you have to remember that cosecant is the reciprocal of sine. So we'd want 1 divided by the sine of that 21 degree angle. So that's the only way to get your cosecant, is to use that reciprocal fact that it's the reciprocal of sine. Hit enter and we get 2.7904. So there's no real work to show here. Now for this next one, 5 pi over 12, you don't see that little degree symbol, so you have to assume that this is radians, and it's kind of a giveaway when you see that pi in there, but for these next 3, there's no degree symbol either, so all of these are going to be in radians as well. So unless you see that degree, you have to assume that you want to be in radian mode. So I am going to have to convert my mode back to radians. So put your cursor over it and highlight it, hit enter, and then we can quit. And I wanted tangent of 5 pi over 12. So I'm going to type in tangent 5, hit my pi key, whoops, divided by 12, and make sure you're using the actual pi key and not some sort of approximation, and we get 3.7321 if I round off here. Okay, and then the last 3 here, same thing, there's no degree, so we're just going to be using that radian mode, which we're already in, so it's just a simple question of doing cosine of negative 1.62. So this is going to give me negative 0.0492. And then if I want cotangent, there's no built-in cotangent. So I'm going to have to do 1 divided by tangent. I'm going to have to use that reciprocal button, or reciprocal idea. So I want to do 1 divided by the tangent of 14.2. And we get negative 0.0629. And then for the last one, it's a secant, so that's the reciprocal of cosine. So we're going to have to use 1 over cosine of 8.14. So we get negative 3.5444. Okay, so there was a lot of information in this lecture today, but most of it comes down to this unit circle. You really want to maybe make some flashcards for yourself or practice drawing this unit circle from scratch several times so that you can really start to commit to memory all of these terminal points as well as all of these placements of your angles in radians and in degrees. It's a really good idea to have all of this really truly memorized so that you're not having to struggle over thinking about what's the correct angle and what's the correct terminal point. That should be the easy part. And there will be questions on tests and exams that do ask you to find these values from memory, so you won't be allowed to use your calculator. So please, please, please practice that unit circle. Alright, that concludes our lecture on trigonometric functions using the unit circle. Good luck.